Phone. So I'm going to talk about keeping the smoke in. This actually started off with an idea to do a little talk on fuses and overvoltage protections and those sorts of things, but it's morphed into something a little different because as I started planning it, I thought, well, on some of the Facebook groups I hang out on, Arduino and things like that, I see people repeatedly having the same misguided ideas about doing certain things. So I thought, okay, and sometimes I wait and say, no, look, that's not really the way to do it. And of course I get flamed by people who know a lot better than an engineer with 55 years experience. Some of them are 17. But there are certain things that I do sort of see repeatedly. So I've tried to list those more or less in a priority order, and that's how I'm going to treat them. So this is the things that you're most likely, I hope, most likely to encounter just as a hobbyist, cobbling together stuff with Raspberry Pis and Arduinos and this, that and the other, and the sorts of typical reasons why you may release a bit of magic smoke. Because if you try hard enough, I'm sure you still will. So first thing is just what happens to the batteries connected back to front. And I did this board recently, the EMG board, which some of you have seen. Some have signed up to get a copy of it, electromyography amplifier board. That's battery powered, and it would be fairly easy to put the batteries on back to front even momentarily and blow something up. So in that I've put some reverse polarity protection. There's two basic ways of doing that. Whoops, that wasn't meant to happen. A series diode, so that's a power supply, and that's maybe the load, your device, a series diode, so that if the polarity of the power is connected back to front, the diode will just block it. The other way to do it is with a shunt diode. And what basically happens there is if you put the power on back to front, the diode's going to turn on and going to suck all the power out of the power supply, which could be dramatic if it's a 100 amp power supply. But if it's a small battery, it may not be terribly dramatic. And you would very typically add a fuse into that circuit. So the current goes up to maybe 10, 15 amps very momentarily. It won't damage the diode if it's brief, and the fuse will blow. And you'll say something rude and you'll replace the fuse and you're good to go again. In the little EMG amplifier, I didn't even bother with the fuse. Nothing. I reckon the batteries probably just can't provide enough current to... Oh. Oh, there's a gremlin somewhere. The battery wouldn't supply enough current to damage the diode in all probability. If it did, the shunt diode, if it fails, is probably going to fail to a dead short anyhow. And so it will still protect the circuit and maybe do a bit of harm to the battery. And in worst case, it may blow out a little bit of printed circuit track. But it's a lot better than having a whole bunch of circuitry blowing up. So that's reverse polarity protection. Just a couple of tips there. Consider this whole thing really just a few tips from about this, that and the other.
Before you go, David, have you got pros and cons for both?
Well, this sort of, okay, the con for the shunt is that it's going to kind of produce some heavy currents one way or another. So something is going to give one way or another. The con, and that's the next slide actually, the con for the series diode is that a diode will drop some voltage. You're going to lose some voltage. Now, there's this kind of thing that goes around, our diode drops 0.65 of a volt. That's actually just a kind of a rough order of magnitude. In fact, if you look at three common diodes, the little 100 milliampere 1N4148 drops 1 volt at 10 milliamps, up to. 1N4004, your common or garden 1 amp rectifier that you'd use all the time, 1.1 volts at 1 amp. So that's its nominal rated current, it's dropping 1.1 volts, not 0.65 of a volt. And a 5401, which is on the next up the scale, there's a beefy 3 amp thing, again, 1 volt at 3 amps. So the series, I'll go back to that, the series diode there is probably going to be dropping about a volt off the raw power. Now if you've got a 6 volt battery and a 5 volt regulator, just an ordinary 78L05, you're already getting into marginal territory where your regulator may start dropping out. Okay, the next thing is just protecting, typically...
Backing up, you didn't mention shotkeys?
No, I didn't mention shotkeys, too complicated.
Okay.
Yeah. Look, you can get Schottky diodes that drop about 0.5 of a volt, nominally 0.3, about 0.5, but they're a bit harder to get hold of, and yeah. I tend to try and find solutions that are in my component box already, one way or another. So delicate chip inputs, which these days pretty much says CMOS, everything, all the logic chips that we're using these days and microprocessors are all CMOS, complementary MOS. This is a circuit I actually used back in the 70s with just an ordinary CMOS chip here. I didn't even have the diodes. I had a 220k resistor and 240 volts AC going in there. Do not try this at home, but the chip was perfectly happy. And I was just using that to get a mains frequency square wave to time something. Dodgy connector. So pretty much if you're coming from somewhere from outside, a couple of diodes to supply and ground can protect you against a lot of overvoltage situations. Now, a lot of chips actually have the diodes built into them, but you need to be able to really, really read the data sheet to know. At one time, back in the 70s, the data sheet showed the diodes there, so you knew. And that's how I got the confidence to do that trick with 240 volts going in, because I knew the thing was there. I put a big enough resistor, limit the current to about a milliamp or something, good to go. But these days it's not that clear cut what's allowed. Typically the data sheet will say maximum input voltage VDD plus 0.3 of a volt. Now what does 0.3 of a volt mean? It's not plus 0.6 of a volt, which might say a diode. Maybe.
Basically what it means is that there's an internal diode, and if you put in VDD plus 0.6, it's going to turn that diode on and blow it up.
Well, it's going to yeah.
So that's the reason why they put that stick on.
Incidentally, you just reminded me, the other interesting thing, and Bern's not here today, I think it was Bern that had this interesting little thing, that because those diodes are internal to the chips, you can get chips that are powering themselves off nothing. Because the input signal gets rectified and fed to the supply pin of the chip from a square wave going in, 5 volts or 4.5 volts in the CMOS chips, merrily going along doing its business. It's called phantom power. I think Burns had something like that, and these LEDs were glowing and he just couldn't, had a lot of fun trying to figure out what was causing it.
Can I comment on
Yeah.
that? I agree with you entirely there, David, but there are a lot of people who sort of say, look, you're putting your chip in the car and the car has got all sorts of spikes in it and you have to put in zingers and stuff to protect it. No, as you say, almost all of the chips have got the internal diodes, and if you put a series resistor in front of it and it's big enough, and quite often 20 k's is enough,
Yep.
provided you don't get more than a few milliamps going in there.
Yep. Yep.
Provided you get more than a few, limit it to no more than a few milliamps, you can put in 10, 20, 50 volts. And it's not a problem, and it doesn't blow the chips up.
Yep.
So this sort of protection, people can go way overboard.
It's very hard to know exactly where to draw the line with that sort of thing. Yeah. And probably if you're doing it for the military, you wouldn't get away with that either. But
I think if you ask the manufacturers of the chip nicely, they will tell you the maximum input current to any pin. If you ask them nicely, it won't be on the data sheet, but if you ask them nicely, they can go and calculate it for you.
Yeah. Manufacturers tend to be a little shy about specifying too many things, because why would you? And the other thing, I've actually sort of read up on quite a few data sheets preparing this presentation, and it sort of came home to me again that the things they put into data sheets are the things they can test for. They're not necessarily the parameters that are important to you. So that's the other thing. Reading data, I actually learnt more electronics reading data sheets in the 60s and 70s than I did in my formal training. Seriously. And that was sort of on the principle, if it's in the data sheet, it's got to mean something. So I'm just contradicting myself there, really, because I'm saying one side they don't put in the important stuff, but when you've got I still remember the input specs for 741 and 709 op-amps because they were there in the data sheet. You know, input bias current, input offset current, and that's got to mean something. It certainly does. So one of the common situations we get is we've got something that's running off 5 volts, typically an Arduino in your case here, and you want to interface it into something that's running off 3.3 volts, like a PIC or a Raspberry Pi or an ESP8266. Now, I've listed the micro-mite as well because that's the one that I used in this little robot that's not got very far so far. The chips in there, they're PICs, and some of the inputs are 5 volt tolerant. That means it's a 3 volt chip, but you can put 5 volts into the input, and it's designed to handle that. So that's all good. Raspberry Pi, no, you can't do it. The inputs are not rated for 5 volts, so you will very likely probably release a very nanoscopic amount of smoke, but you will very likely smoke the chip or at least damage that particular input, so that's a no. ESP8266, I spent half an hour researching that and there is no clear answer. There is no clear answer on that chip. An early data sheet says yes, you can do it, and we've got this input structure that clamps some sort of snaps or something or other. Later data sheets, that paragraph has been removed. So no one actually knows on the 8266. So it's probably best to use some sort of protection, as the bishop said to the actress. So 3 years and 8 months later. Okay. So here's a fairly simple solution to interface from 5 volts to 3.3 volts that's going to work most of the time. Just a voltage divider. And I've got 3.3 volts across that, and I've got about 1.7 volts across that, and now 5 volts is going to become 3.3 volts, and we're good. The limitation on that sort of scheme is if it's a very high frequency signal, it's going to slow down the signal because the stray capacitors here, and you might need to go to 1.8K and 3.3K. The bad news is unless you've got an oscilloscope and you're able to actually observe it, then you're kind of shooting in the dark with what you're doing there. But that's a simple solution. As I said before, some chips have got diodes in their input structures, which means you can basically do away with that ground resistor because now you're back just to that series resistor thing. And I've done that a couple of times. Quick and dirty. If it's not fast, it works. Joe, are you able to say how many of the chips you can pretty much bank on having diodes? Into the microphone, please.
A lot of it depends. If it's logic, it depends. If it's a logic device, yes, generally. If it's an analog device, no, because analog devices require generally a higher input impedance, and putting back-to-back diodes to the input of a op-amp or a analog device can reduce its performance. Yeah. And so if you're trying to get measure a really sensitive signal, putting diodes either externally or internally weaken the input characteristics of the device. But generally, logic devices generally have them. Yep. And again, if you ask the manufacturer nicely, I want to put up to X milliamps into this pin. I know the pin's rated to whatever. They will say, yes, you can do it on 3 pins. That's it, provided XXXX. Generally, that's information on request only, generally. Yeah. There's, as you know, there's mostly an absolute a maximum in everybody's data sheet. That's not the design parameters, that's just absolute maxims, of course. But there are the ones like these diodes that are not really covered anymore without a special request. Yep. Those people doing 10 million pieces want to save 1 cent on a resistor. Right? If the diode's included in the part, they'll save that 1 cent. But you and I, if we're doing quantity of 1, quantity of 5, quantity of 100, put the resistor in. That's what I would say. Don't give yourself any pain. Or if you're coming up to doing logic conversion as well, I imagine, further up in the thing. Or look at the other steps. Yep. Do you want the pain later on, or do you want those weird things that are happening to your design that you spend 3 days pulling your hair out? And you may as well put it in the beginning, because if your volumes are not large, put it in. The extra 20 cents for that device is probably well worth it, as in a logic conversion device or resistors. Yeah,
yeah. A couple of other aspects of that actually, depending on what the particular device is. It can vary from manufacturer to manufacturer. Now, if it's something like a PIC or a processor chip, yeah, that's one source pretty much. But if you're going into an 74HC logic chip or something like that, what Fairchild put in there may not be the same as what Toshiba put in there or what Philips put in there. They can vary, and they do vary. And if they're Fairchild, usually just stay away. Motorola used to, well, is there a Motorola anymore? I think that's kind of gone. Yeah, all gone now. The other related thing, and Joe mentioned sort of logic devices and analog devices. If you have an analog input, a microprocessor with multiple analog inputs, or an analog multiplexer, overvolting those even by a slight amount can totally screw it up. So I can have 5.5 volts going into the 5 volt input on channel 1, and the reading on channel 5 gets totally screwed up. So there's a lot of feed through in some of the multiplexer chips. You know what a multiplexer chip? Select one of several inputs and feed it into a single analog input. And that's what most of the microcontrollers have got, multiplexer at the front end. Too much voltage into an analog multiplexer and it will just distort the voltage on all of the pins. So then you can't be doing this kind of caper here. In fact, in one of the boards when we designed our boards with analog inputs on, we put op-amp-based active precision diode clamps in, so that the input could not get over 5 volts, not by 10 millivolts. We were that anal about it, which of course was the splat difference. Okay, what about the other way? Driving from a 3.3 volt thing, like say a Raspberry Pi, into a 5 volt chip, which could be a Raspberry Pi driving into an Arduino, for instance, or into some HC CMOS running off 5 volts. What do we do? Now, if you consider that a 3 volt chip, a CMOS chip, when it's high, its output is high, if there's no loading on it, it's going to go to the rail. Datasheet will give you 50 millivolts clearance, but I think that's just a bit of safety margin for themselves. It will go to 3.3 volts. Arduino, using an Atmega 328, has an input threshold of 0.6 times the supply voltage, maximum or worst case, which is 3 volts. So the 3.3 volt output of the Raspberry Pi is 300 millivolts over, this is the high voltage, the low is always low, that's not a problem, but high voltage is 300 millivolts margin over what the Arduino requires. So on the face of it, yeah, it's not a lot of margin, a bit of noise might upset it, it's not too bad. But the problem is, are your power supplies actually 3.3 volts and 5 volts? If your 3.3 volt chip power supply is 5% low, which it's allowed to be with a regular regulator, and the power supply to the Arduino is 5% high, which it's allowed to be with a 5% ordinary 3-pin regulator, you're going to have a minus 15 volt millivolt margin. It'll never get there. So this is the old, shit, the prototype worked fine, and we made 2,000 of these, and now suddenly they're not working. And it can bite you in the bum as a hobbyist too. It can be working one day and you replace the regulator for some reason because you've smoked it, and suddenly the thing doesn't work anymore. Or you get a slightly noisier environment. So actually, you can't do that, and be safe and know that it's going to work. So no cigar on that one. So we actually have to start going to level translators, some sort of active circuit that shifts the voltage from 3.3 volts to 5 volts. And there are a few possibilities there. First one, a good old BC547, or any old NPN transistor you've got lying around, a 2N2222A or something like that, in what effectively is a common base configuration. The base goes to the low voltage through a resistor. The emitter goes to the output of the chip. When the chip switch is low, this is brought down to close to ground, and current flows through that resistor and pulls that pin down. The transistor saturates and you're good. When the output of that goes high again, it all just floats up, and that resistor pulls the input of the 5 volt chip up to 5 volts. Sweet, works wonders, nice and simple. So that's something, you can find a BC548 in your junk box. If you can't, there's 50 of them out there in the shelves. Easy peasy. Okay, and a couple of resistors. The values are not super critical. I've got a ratio of 10 to 1, which means the transistor's getting well driven. This guy is being called on to sync half a milliamp, 10k into 5 volts, so it's not straining, and it'll all work fine. Not super fast with 10k, but if you want to go super fast, then you've got to do something a little more fancier. But probably about the only time that you'd be going super fast in a hobby situation would be if you're sort of using I2C or SPI bus or something like that. You're starting to clock along a little bit. But you know, you're not working at gigahertz frequencies in the hobby domain, generally. The next one is basically the same circuit, but you're using a small FET, a 2N7000 instead. You save one resistor at the cost of a 2N7000, which will probably cost you more at JCAR, and it's a bit rarer. I mean, most people have got a BC5, something kicking around in the junk box. 2N7000 you may not have so readily. This works because the turn-on voltage of the 2N7000 is about 3 volts, so it's just about guaranteed to work. I must confess I've never done it myself, but I've seen it around quite a lot. Incidentally, the 2N7000 actually has a diode across there, going in the other direction, so it can also work as a bidirectional level translator.
Clever pilot, using that diode.
Yeah. Yeah, it can be a bidirectional. Well, I haven't covered the bidirectional because that's where we're getting a little specialised. Next possibility is to use a 74HCT, and the T is the important thing, logic chip. Now you can buy one of these, 6 in a package for about 30, 40 cents on eBay and $3 or $4 at JCAR. HCT is designed specifically to be compatible with the old TTL logic, so it's got an input threshold of 2 volts, not 3 volts or something like that. So it will switch at 2 volts and drive your 5 volt circuit. The downside is it's inverting. So a high there becomes a low there, and vice versa. If you can cope with that, fine. Which may mean a slight change in your software if you're writing, whatever. Or you can put 2 in series and invert it back again. That one will be fast, by the way. That one you're not going to have any speed problems with, but it is unidirectional. And the last one is you can simply go onto eBay and buy yourself some level converter devices. That probably doesn't shout very well, but they're very cheap. There's 4 channels or something. I've never played with them. I might have bought some, but I've never used them. Yeah, tiny little things. Yeah, and those, of course, are convenient if you're sort of plugging together stuff with an Arduino with jumper leads and stuff like that. So that's another option. So there's quite a few options for doing that particular job, switching from 3.3 to 5 volts. depending on your needs. Right, now the other mistake I see people making is in driving the gates of power FETs. Now power FET, that's not a 207,000 little tiddler, but we start getting into some of these big 5, 10, 20, 30, 100 amp FETs and switching them and wanting them to switch hard and fast, you've got to, it's not simple. One of the miswordings I often see in the Arduino Facebook groups is, that will be enough voltage to trigger it. There's no such thing as triggering an FET. An FET, as you've raised the gate voltage, will slowly turn on, gradually turn on. There's no snap action or anything like that. It's a semi-linear device. And you've got to treat it with a great deal of care. So if you look at the specs here, it's got a gate threshold voltage there. I've even crossed it out, 2.5 volts. Oh, 2.5 volts is all it needs. Yeah, to conduct 250 microamps. That's just the point where that's a testable point for in the factory probably. We put that gate voltage in and see that it's conducting 250 microamps. We know it's an FET, it's not a lump of sand. But that's about all. So that's pretty meaningless. Now, what does matter is something like the drain to source on resistance. 3.8 milliohms, which is not much resistance. Well, this particular device is a IRL 7833. I think it's a 100 amp rated device. It's just one I happen to, someone was using one on one of these Facebook groups, in fact, and wanting to trigger it. 4.5 volts at 30 amps. 3.8 milliohms at 10 volts on the gate and 38 amps. So if you want to pull 38 amps out of it, which is a lot, but think in terms of supplying 10 volts to the gate, not puny little 5 volts. If you're happy with 30 amps, 4.5 volts on the gate will do it. Because it's got that L in the part number, which means it's a logic level device, designed specifically to work off low gate voltages. That doesn't mean it's going to do everything with 4.5 volts on the gate.
Have you seen power?
He's got a permanent microphone.
Yeah, I've got it here. Have you seen FETs with a 3-volt drive? Because there's a lot. There's just about every logic level FET has a 4.5 volt characteristic, but I haven't seen many with a 3.3 volt drive.
Right. No,
if you haven't seen anything,
look, it's not something I've researched very much, Joe. I'm kind of not that much into FETs. Yeah, John. Hang on.
Look, a couple of comments. I have seen a handful of FETs that are quite low threshold voltages, 3 volts and below, but you have to search for them. Look, the other comment, David, is sort of going right back to what you said at the start and stuff like that. I have a rule of thumb that in many cases I try and not run a device anywhere near its limit. In fact, I usually use a factor of 2. So if a thing's rated at 10 amps, I'll try and not use it above 5 amps or whatever, because usually what happens is the manufacturer is choosing a specification that looks good on paper. Oh yeah, this runs to 5 amps, but you look at every other specification when it's running at 5, let's say the high value, say 10 amps, it's bloody awful.
Yep.
And so, for example, and I think it's a great one there, you know, the first one there, the gate to source voltage of 10 volts, you're hard pressed to find some logic that's going to drive it. But you can find lots of 5 volt logic around the place, and guess what? The thing has been rated at 30 amps, but if you're only expecting half of the 38 amps out of it,
Yep.
the 5 volts will drive it easily.
Yep.
Same with the diodes. You know, you were saying at the start, well, yeah, a lot of the diodes are saying that they're 1 or 1.1 volts, but that's when they're pushing the current up. That's the limit of their current. If you went to half of their current, you'd find that they'd be back at 6.6 volts. So there are lots of things. You know, you don't run your car flat out. Don't run your electronics flat out if you can avoid it.
Well, with my car running flat out would be about 20 miles an hour. So yeah, no, you're absolutely right, and you have to. I'm not sure how to put this. One of the implied mistakes I see on the forum, the Facebook thingies I keep on talking about, no one there goes and reads data sheets. Goes and reads data sheets. Now, I don't know why that is, if they are scary and threatening or what it is, but maybe it's just too many technical. I don't know. Anyway, for me, the data sheet is always the first port of call, and to interpret the data sheet and really read in what it all means. But Peter, do you?
I think the answer to that may be simpler than you think. It's just that when people read data sheets like this, they're not exactly sure what a static drain to source on resistance is. I'm still scratching my head onto exactly what that means. And I think most people playing with Arduinos, and like you said, they really enjoy the code side of things, and they get a digital chip, and they are expecting to do exactly what you said, to switch it.
Yeah.
And I accept that. Yeah, transistors obviously that they need to be saturated, and that is a very analog relationship. And I mean it's natural. It's not code. It's electronics. But that's why. And I'm still daunted by data sheets like this as well. Even though I probably shouldn't admit that. I should have the training for it. But
I guess the other thing is too that the data sheets. I mean, I've only selected 4 or 5 lines out of a data sheet here. There's probably that much stuff, and how do you know how to pick the eyes up? I mean, with 55 years experience, the eye just goes looking straight for the crucial spec. Straight off. I'm sure you do the same. I'm sure Joe, if he's not playing with his phone, does the same. Caught. You're going to lose your microphone privileges, Joe.
I'm looking up a data sheet.
Yeah.
The other thing is that little note number 4 could well be quite important. On the 30 app.
Oh, note 4.
Oh, okay, no.
Yes. Note number. You're quite right, and I didn't deliberately omit that because I tend to only read the footnotes after the product comes back with smoke coming out. No, seriously, you do read those notes and all that. But no, Peter, it's a good point. It can be quite overwhelming to see all that stuff, and I guess that's why people just don't at all.
We just let the smoke out. I just let the smoke out and then figure it out later.
Yeah. Okay, what have we got next? I'm not sure. Now the other thing is speed. The input impedance, the gate impedance of an FET is infinite, isn't it? It draws no current. Absolutely wrong. When you're switching that gate on and off, it is drawing potentially vast spikes of current, because you've got some capacitance between the gate and the source. You've got capacitance between the drain and gate, which is called millicapacitance. Whatever the voltage gain of this device from there to there, from the gate to the drain is, whatever the voltage gain, that stray capacitance is multiplied by that amount. So if you've got a voltage gain of 100 and you've got 1 picofarad, you've got 100 picofarads. In fact, you're more likely to have about 47 or 50 or 100 picofarads there, multiplied by 100. So looking into the gate of one of these big juicy babies, you're going to have several nanofarads of capacitance and equivalent. Serious amounts of capacitance. And you want to switch that from 0 to 10 volts maybe really, really fast. Because if you're just pumping in 1 milliamp or 100 microamps, that capacitor is going to charge up slowly. The device is going to start to turn on, the current will rise, the voltage will drop, and the heat dissipated in the device is the voltage times the current. So every time it switches, you're going to get this big spike of energy being dissipated in the transistor. Do that 100,000 times a second or 500,000 times a second, there's going to be smoke coming out. There really is going to be smoke coming out. So you've got to belt that gate really, really hard if it's in a switch mode power supply or a PWM speed control for a big beefy motor or something like that. You really got to thump it hard. It's serious stuff. And I once had a box full of dead FETs to prove it when I developed something. It's real. It's very real. So you've got to have a solution. If you're going really bleeding edge stuff and making a high power supply or controlling a fairly decent motor, buy a gate driver chip and study it. If you're doing, say, PWM out of an Arduino to drive a chain of LEDs or something like that, you can possibly get away with something like this. Logic level FET, that would have to be, and my favorite old HCT04 again. Each of those stages will sort of spike out at about 20 to 40 milliamps or something like that when it's switching. So you've got maybe a couple of 100 milliamps of potential gate drive there. So with reasonable, I can't give you actual numbers, but if you're sort of driving an amp or two and you've got a fairly beefy FET, and I mean even this fellow here was, I've only discovered it the other day, and it was $5 for $8 on eBay or something like that for a 100 amp FET. It's like, why wouldn't you not go to JCAR? So that's a good. I've done that once or twice. Just use some gates like that, CMOS gates. And on the right, so if it's a 5 volt input, you can even use one of these octal bus driver buffers, which are good for 50 milliamps per stage. Parallel them all up, bang it away. That'll work. Driving relays. We probably all know that if you're switching a relay off a transistor, you'd better have a diode across the relay coil. Anyone not familiar with that? Okay. When I turn on that transistor, it's like a flywheel. A coil is like a flywheel for current. When I turn that transistor on, current is going to flow down here. We always look at positive current, throw it down here. So it's going that direction. When the transistor turns off, that current cannot stop instantaneously. So it's going to continue to flow. It can't go there anymore because that's off, so it's going to go along there, and it's going to go there, and it's going to circulate like that. And that energy that's stored in that coil is slowly going to dissipate in the resistance of the coil, because every coil's got resistance. If there was no resistance in the coil and a perfect diode, the current would go forever. And you would have yourself an MRI machine. So that energy has to be dissipated somewhere. If I don't have any protection here, if I cover up all those things, if I don't have any of those things, that voltage on the collector is going to fly up to whatever voltage it takes to get rid of that energy. And where will the energy go to then? It will go into the transistor when it hits the breakdown voltage of the transistor. And what will happen to the transistor? What happened to me once? A little lump of plastic actually flew out of the transistor case as the die embedded itself in the ceiling. Yeah, it actually wasn't a relay, it was a little tiny little audio transformer many, many years ago. So what happens with the diode there? The transistor switches off. Because there's fairly low resistance here, the current will circulate for quite a while. And die off, it might take 100 microseconds or something like that to die away. If instead of the transistor, the diode, I use a Zener diode to ground, what will happen, say that might be a 50 volt Zener and a 60 volt transistor. So the voltage here was going to fly up to about 50 volts and the Zener is going to take over and the current will flow. But now we've got that current, which maybe it's a 50 milliamps in the relay coil. 50 milliamps times 50 volts is 2.5 watts. The energy is going to dissipate very quickly because it's dissipating in the Zener diode. Whereas here it's dissipating only in the resistance of the diode, 1.2 volts in the diode, and there. So it's relatively slow. With the Zener it's very much faster. And believe me, that can be significant. The other way of doing it is with a resistor and a capacitor. And the sums for doing that are probably a little bit complicated, but it can certainly be done, and you can get a similar, fairly rapid quenching effect as you do with the Zener. They're probably not quite as fast. So I haven't seen the resistor capacitor done very much. It can be done with AC coils, of course, when it's not DC going through them, but AC. In fact, it's the only way, just about the only way of doing it. But it can be done. So the Zener tends to be the preferred if it's important that the relay switches off quickly. Relay contact certainly quickly, rather than slowly. Protecting the relay contacts on the other side. Yes, Rob.
David, can you refer that situation back to the Arduino case, driving a relay from an Arduino output? What's happening internally in an Arduino case?
Oh, well, this would be, I just always use a triangle to denote a thing. So this can be your Arduino. So it's coming out of the Arduino through, I didn't even nominate a resistor value there, but maybe a 1K resistor or 5K resistor or something like that. So that goes high. In the code, you turn the output on high.
So I shouldn't be, for example, driving a relay directly off an Arduino output without putting some diodes or...
Only if you,
coils?
well, no, you'd want some diodes, and probably only if you paid a lot of money for the relay to have such a sensitive coil that it can be driven off 10 or 20 milliamps the Arduino is capable of.
Very sensitive relay.
Yeah. You can get them, but it tends to be expensive. Oh, okay, now if you've got a counter experience, tell me. Yeah, come on.
I guess wanted to hear what your
Yeah.
thoughts were in that situation,
Yeah.
because I've been doing it without
The
knowledge of what I should be doing,
Yep.
and I haven't burnt any relays out. Or
the output of the Arduino, the output he's talking about the GPIO pin, right? The output of the pin output. Typically, the Arduino IC will have a maximum total of number of pins. So if you drive 3 relays, you'll have a maximum, might be 100 milliamps total before the chip melts down. So you might be able to get 10 or 20 milliamps out of a pin, out of a GPIO pin to drive the relay. The relay will have some current. But as you start loading up other GPIO pins, you then start to exceed the whole IC's current consumption requirements. So one might be okay, and if it's a 20 milliamp relay or a 10 milliamp relay, then you might be lucky. But then as you start to increase an LED 5 milliamps, another LED 5 milliamps, driving a siren, as all those things add up, the overall load on the IC starts to become significant.
so does that mean like a relay board, a driver board for a relay will have that sort of protection built into it?
Yeah, the ones you buy on eBay, yes, they definitely have that protection. They tend to also be optically isolated, by the way, which is pretty cool for something that's so cheap.
Yeah. Particularly for people who are doing one-off or small quantities and not doing serious industrial design, I like the idea of each wire or interface that's going off a board, be it either input or output, has got some sort of isolation chip or interface, if you like. And so, as David's put up there, a resistor and a transistor, they're not that expensive. And so they are the devices that pop if something goes wrong, rather than your whole Arduino or your PIC or whatever.
Yep.
And also it tends to give you a much better fault finding capability. So I like the idea that, particularly if a wire's going off or an interface off a board on the input or the output, then it ought to be going into a sacrificial piece of electronics first. And it might be a buffer amplifier on the input or a buffer logic chip, in which case it might be the your hex inverters or something other like that. Similarly with an output drive, logic or analog, so that particularly in the development side of things, that's when you'll pick those things up. So I think that's just good practice.
Yep. Yep. So I'm still a little intrigued, Rob, about your relays. You must be buying 5-volt relays.
No, it's through a relay board.
Oh, relay board. Oh,
It
okay,
is
right.
through a relay driver board.
Yeah,
so,
okay,
yeah.
yeah.
It's covered.
It's got that circuit in it. Yes.
Yep,
Yes.
Thank you.
Yeah. Yeah. Look, and look, in the hobby end of the game, I mean, it is so common these days that you can buy a little board that's got all the stuff on anyhow, and it doesn't validate what I'm saying, but it certainly is the case that that's what happens very often. So, oh yeah, now protecting relay contacts. So I've got a hypothetical illegally wired up mains here, driving a mains motor, and the relay contacts. And this motor here has got lots of back EMF, and it's got lots of inductance. And every time the relay contact closes, that's fine. But when it opens, all this voltage is generated, and you get arcs and sparks flying across the relay contacts. And you do that, you switch that on and off about 500,000 times, then you break the relay open and have a look, and the contacts look like a moonscape. I've done it. Actually, we did that once. So how do you suppress those arcs and sparks? This is AC, so you can't use a diode directly. You can put a resistor capacitor across it, and that's a pretty good way of doing it. Very, very common. You can now now if you're doing this, one, don't do it at home. Two, come and talk to somebody with the experience before you start doing that sort of thing. But the capacitor is probably going to be something like 100 nanofarad, but it needs to be high voltage rated. And one of the cool tricks is, or maybe a 10 nanofarad 1 kV disc ceramic or something like that. That's not going to come to any harm. The resistor also needs to be rated for 240 volts, which is not your little piddly 1/8 watt resistor that you buy at J-Car. It's going to be a 1 watt or bigger, preferably carbon composition, which are very hard to get these days. They can withstand that voltage and that trauma of sudden currents going through it. And there is also a device you can buy called, we used 1,000 of them at one stage in spa bath controllers, which is called an XE1201. We were buying them by the bucket load, and it's a resistor and capacitor all in one neat little package, just drop into the board. I actually looked them up the other day, and they're horrendously expensive to buy nowadays in small quantities, but we were buying such large numbers, it was well worth it. A MOV, a metal oxide varistor. These are the things that are usually when you buy you go to Officeworks and you buy the power strip that's protected against for your computer with built-in surge protection. That's what's inside it, a MOV. So if some spike comes down the mains, the MOV will turn on and limit the voltage. Maybe rather than going up to 500 volts, it'll stop at about 350 volts or something like that, and hopefully protect your computer. Very bad idea to use those in this situation because a MOV has a finite life. It can only take a certain number of hits, and then it goes to God. It dies, and it's a MOV no more. Very MOVing story. Then the final thing is something called a TVS, a transient voltage suppressor, which is kind of like this version. They come in AC and DC one. This is an AC one, 2 Zener diodes back to back, and it will start to switch on at some specified voltage. And they're not ordinary Zener diodes. They're Zeners with really large, chunky junctions, so they can take a big energy hit and survive and just brush it off and carry on and fight another day.
They're not cheap.
They're probably not cheap. We used to use a lot in, we were making alarm panels for Chubb Fire, and we used a lot there. But I think they were smallish ones, about the size of a 1N4004 diode, and unipolar ones. But buying them for 1,000, it's a whole different matter.
Can I go back to your left-hand one, the RC one?
Joe and I ought to sit together.
Good idea. Yeah, Joel will have to stay awake now, won't he?
Yes. Yeah, the capacitor there, as David said, it has to be a special one. Part of the reason that it has to be special is that it's not only rated for 240 volt AC, it's rated for 240 volts AC forever,
Yep.
long term. I came to grief when I had a capacitor that was in a situation rather like that, and I didn't know about these sort of specs. And I found a capacitor that was rated at 400 volts. Now, 240 volts AC translates
Peaks at
into
about
320 or something or other, is it?
Yeah.
So it was, the capacitor was well inside the specifications, being 400 volts rated DC. And after it had been in service for 6 months, it blew up spectacularly. As I recall, one of the specifications is called X2, I think it is, for the high voltage capacitors. So the capacitors specifically made for long-term connection across the mains. You pay extra for them, and that's why they are special. And if you don't get those things, you're asking for a fire.
Yep. Which is sort of why I said a 1 kV ceramic as well, which is probably pretty okay, but way overrated.
So what happens is that, particularly with a capacitor like as you said, maybe 100 nanofarads and stuff, there's a significant amount of AC current going through that capacitor. And so the capacitor is being heated up. Although it's a capacitor, you think of it not actually dissipating power, it's got a significant amount of power going through it that's heating up through its loss resistance. And so it actually gets quite hot. And so it's actually a thermal rating of the capacitor. And so it's the sort of thing that you turn it on, and after half an hour it's quite hot and it blows up.
Okay, thanks. I learnt something new then. I thought it was more the scroll wheel just moves the page. I thought it was more a matter of the. By the way, they're called X-rated capacitors. You're dead right. I'm not sure. But X-rated are rated to be across active and neutral. Then there's Y-rated capacitors, which are rated to between active and ground and neutral and ground. And they're used in filters, in RFI filters and things. And you better be using that. Particularly, well, no, you just better be using that.
Just Google X-rated and you'll get your answer.
Why?
Sort of club.
X-rated capacitor, not X-rated capacity. Yeah. So, look, in a sense, this is territory that you shouldn't go into as a hobbyist.
Yeah.
Yeah.
Let's not say an absolute no, but for Pete's sake, talk to someone.
Yes.
Connecting things up and dealing with mains is not trivial, and it's the sort of thing that grief is made out of.
And jail time.
Yeah. So, it can be done with the right knowledge, but for Pete's sake, if you don't know a lot about it, come and talk to someone and get some good knowledge.
That's what we have the club for. Ta-da. Okay, now, the snubbing that I use on the coil can affect the life of the contact. I said before, if I've got a diode across the coil, when the transistor turns off, the current continues to circulate and dies slowly in the coil. Now what happens with the contact? The pressure on the contact is reducing, and the contact, you probably can't see my fingers, the contacts open slowly. And as they open, the spark comes up and it slowly drags the spark. Can you see that? It's slow. I can't make sparks between my fingers, but I can make little animals and all sorts of things. It will drag that spark out and it will burn the contact. If the contact opens suddenly, there's less time for the spark to generate. Quite literally. So that's why, and I go back to that other slide, the Zener diode in those sorts of situations is far preferable to the ordinary diode. And that one there, if you use it as a sort of halfway house compromise, it's a compromise because the current decays exponentially, so it's going to stretch it out more. Whereas the Zener, that's dissipating all the energy straight away. So coil snubbing, and we had cases in my business where we had measurable, observable differences. And so after a while we said, okay, if we're using a relay, we're going to snub it, the contact with a Zener whenever we can. The very same thing, actually no, I'm going to say, slightly different, but if you're, say, controlling a solenoid valve, you're probably better off using a Zener than a diode because the valve is going to turn off more sharply. So just something to keep in mind there. Or you have an option to use nothing at all. Now we actually had a case where we were doing, I forget exactly which project it was, but we were driving an inductive load, a known inductive load, and we actually got an oscilloscope and we put it on, we just a little series resistor so we could see the current, and we did it with and without an RC snubber, and we could actually see that the stress on the contact was going to be less without the snubber than with the snubber. Now it may be that we'd got the wrong values, I'm not too sure, but we in the end, and we then did a long-term test in that particular situation, and we were better off without the snubber, but with fast turn-off, than with it. Now don't ask me with the fast turn-off where that energy went, I honestly don't know. But
Wouldn't you use a solid-state relay now?
yes, well, no, yes and no, yes and no. It depends on the application. There is still something very comforting about two big lumps of metal that come crashing together. There really is. And
Makes you feel good?
makes me feel good. Oh yeah, I get off on that. I really get off on that. Yeah, yeah.
The question is, does the solid-state relay handle inductive loads?
Well, there's all sorts of things. A solid-state device is always going to be at the boundary more fragile. A relay contact, you can abuse it maybe occasionally, and it's like, it's only a flesh wound, not even a flesh wound. Come on, do something real damage. Whereas a solid-state relay, particularly if you're mishandling it, is fairly fragile. So there are horses for courses.
For a hobbyist, though, it's packaged a lot safer for doing this
Yes.
type
Yeah.
of work
Yep.
that would far outlay
Yeah. Yeah.
the smashing
Yeah.
pieces of metal
Yeah.
together.
Pay
Look-
a bit more money for some good contact material.
Well, that's the other thing. Yeah. Yeah. Yeah.
If I can just say, if you're going to get a solid-state relay, one from a known, trusted, validated source.
Not eBay.
Right, so because
Yeah.
you know a trusted one will be, you'll be right, and will have all the generally have all the UL and safety ratings for it,
In terms
for
of safety, yeah.
for flammability and
Yeah.
catching fire and all those sort of things.
Yeah.
The second point is that relays have a mean time between failure. So if you operate them a million times, they might not operate a million and one times, whereas solid-state relay has infinite number of turn-off and turn-ons.
Yeah. Yeah. And that's the horses for courses thing. In the short term, within its life, a relay is probably more robust than a solid-state device, but it will wear out. And very, very early in my career, we got a contract with Main Roads Department in WA to make the no right turn flashing signs. They had a neon sign in a big box and a big transformer, and they were flashing it. And even then, as a young pup, I sort of thought, well, relays are nice and solid, so I thought, okay, I'm just going to use a relay. Boom, boom, boom. 50 flash, whatever it was. They flash them in Perth. Here they don't, I think. Then I looked at the data sheet really, really carefully and looked at the lifetime of the relay. And I figured out that the relay I had in mind, and any one I could find, was going to last for about 3 months. So I had to go and use a triac, and in those days to trigger a triac you had to use a pulse transformer. We didn't have opto-isolators in those days, and it was quite a big, it was a lot more complex to do, but they survived. For all I know, they're still flashing away in Perth. But the relays would have, so horses for courses. Other cases, yeah, we did the controllers for the big carrier rooftop air conditioners, the big things you use a Chinook to lift them in place on top of a factory building. And the engineer there, a Polish guy, Joseph. He was absolutely PITA, but he was really, really good because he was a PITA. And he insisted the relays, our output was a relay driving a contactor. Bloody big thing like that, clunk, 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 driving the outdoor fans. So you can imagine how big this thing was, because the fans had a dirty big contactor like that to drive them. And our little relay was driving that. And he insisted the relay has got to be, and he'd done his sums, it's got to be good for 200,000 cycles. And so we got one of the contactors, and we got the relay we were proposing to use. Hands up if you heard the story before, it's one of my favourite war stories. And we had a little trolley which we set up in the factory with a splat controller just going click, 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 click. The contactor had auxiliary contacts on it for feedback, so we fed that back into the splat, and we had a little counter, an LCD set up to count, display a count, and we set this going. Every morning I'd come into work, open up, click, clack, click, oh God, click, clack, click, clack. We covered it in rugs, we covered it in cardboard boxes, we wheeled it up to the far end of the factory, the whole bloody thing, click, clack. After about 6 months, I came in one morning.
Perfect quiet.
Beautiful silence. Oh, it was lovely. Thank goodness that B thing has finally failed. Now, the contactor, it had this sort of Bakelite-y body, and there was a sort of square thing that was moving backwards and forwards in a square hole. There was actually Bakelite powder coming out of that hole on the contactor. And when we investigated, it turned out that our relay was still perfectly good. The auxiliary contact on the contactor had got some of the shit in it, and it wasn't making contact. That was why it failed. So it had done 2 million cycles, and he wanted 200,000 cycles. So we said, okay, good enough. That'll do. So yeah.
I was just going to add another thing between solid-state relays and metal contacts is your metal contacts have got a guaranteed low leakage current, whereas
Yes.
you're not so sure about your solid-state relays. So there's a real safety issue in there, and you would say under all circumstances you should never have a control system where something's activated with the mains and have people hanging on the mains. But if in that case you have, you'd be much happier, people connected to the mains, you'd be much happier having not having a solid state relay.
Notwithstanding,
metal.
John, that if you've got an RC snubber on there,
True.
you've got a hazard.
Yes.
And I wouldn't really bank my life on one of those guys either, but that would be maybe 100 microamps leakage. It would tingle you, not hurt you.
Yeah.
Yeah.
I just got some pros and cons between relays and solid state
Yep.
in industrial applications.
Yep.
Solid state relays sometimes don't draw enough current, so the device that is trying to turn it on doesn't sense enough current, and it happens a lot in industrial, so you end up having to put a resistor across it, so it actually draws more current.
Yep.
So although you have benefits of it,
Holding
you've just got to
current.
watch that.
Yep.
And the best usage of a relay is on long cable runs. We've got a lot of EMI where you only need a few milliamps to turn on a solid state relay. A relay, you would specify a 12 or 24 volt. That's why industrial uses 24. In power stations, they use 48 volt relays.
Yep.
Just because to get EMI induced in the cable at 48 volts at enough current to turn on a relay is quite high. So that's where the isolation comes in long cable runs. So if you do have a long cable run close to VFDs and that sort of thing, a relay is great at the end of that cable.
Don't start me on VFDs. And Sparkies that don't use shielded cable on the inputs and outputs. So I've got a note here then. Sorry, was that? Yep. Note here about using the right contact material. I could tell a couple of war stories about that. And as a hobbyist, you have fairly little control over that. You're going to go to JCar or something or eBay and you're going to buy the relays and settle for what you've got. But there are contact materials and contact materials. Probably as a hobbyist, the one thing that you need to be aware of is that you can't use a 10 amp relay to go switching a 1 volt signal from a sensor. it's not going to work. Because those lovely metal contacts that are designed to handle lots and lots of current are going to oxidize from sulfur in the air and all sorts of stuff. And after a while, they're going to have this film on them, but when they come together, nothing's going to happen because they're insulated from each other. And the bigger the relay, the bigger and hairier the relay, the more that's potentially a problem. So if you're going to be switching small signals, the thing to do is either buy a signal relay or a reed relay. And a reed relay will, because it's a little vacuated tube, it's got gold-plated contacts and stuff like that, it will handle low signals. Or a relay that's designed and rated with gold-plated contacts for switching low currents. We won't even go into RF because I don't know. You'd know more about the RF relays than I do. Hopefully.
I didn't hear that. I'm sure you wouldn't insult me.
No, it's okay. Okay. Yeah, I say you're the RF guru.
Oh, good.
Yeah. Yeah. So there's actually relays could be a whole topic in itself. Easy peasy. So I'll move right along here. Right. Your next source of smoke is heat. Devices getting too hot because you haven't allowed for the heat generated. So this is another case where and I've seen professionals making this mistake. Oh, it's rated for 500 milliwatts. It should be fine. So Commodore Garden BC547, the little transistor before, total device, it's rated for 625 milliwatts dissipation. Well, that's okay. That's quite a lot. I won't worry about that anymore. I'm only dissipating 500 milliwatts in it. Then there's this spec here, which is thermal resistance junction to ambient, which is how many degrees C the junction temperature, the guts of the thing is going to rise for every watt dissipated inside it. And the figure is 200 degrees C per watt. So we're going to do the sum. 625 milliwatts, 0.625 watts, times 200 degrees C per watt equals 125 degrees C. So the junction inside is going to be 125 degrees C hotter than the environment, the ambient. If we're in 50 degrees C ambient, you never design for 25 degrees C. In fact, 50 would be a pretty kind of cool number. When I was designing loop detectors for traffic lights in Perth, the case sitting on a traffic standard pole was up to about 60 degrees C in direct sunshine. That was the operating temperature from get-go inside the aluminium box. It's going to get, so at 50 degrees ambient, which is just inside your enclosure you've beautifully built down in the workshop, 175 degrees C. Now the rating is 150 degrees C, so you're violating the rating, but more importantly, I think I've got another overlay for that. It's interesting how this is a PDF, how it gets rendered. Every 10 degrees C in temperature in a semiconductor roughly halves its lifetime. You've probably, Joe, come across similar figures. It's kind of a rule of thumb. Every 10 degrees C. And I think in sort of biology or chemistry, yeah, every 10 degrees doubles the speed of a reaction, roughly. Good rule of thumb. So if I've got a device running at 150 degrees C, let alone 175 degrees C, compared to running at, say, 90 degrees C, that's a 66 doublings, that's 32 times shorter lifetime. So it's not just a matter of saying, well, I'm allowed to go up to that limit and that's it, I'm going to run it there. Its lifetime is going to deteriorate, which may not matter to you as a hobbyist. If you've launched something to Mars, it's going to matter a whole heap. But it's something you need to keep in mind. So failing to properly heat sink devices or allow for the internal heat is, I think, a fairly common trap that hobbyists fall into. So a sort of vague rule of thumb, in a little TO92 transistor like a BC547, If it's coming out at more than 200 milliwatts, you need to start doing some sums and thinking about it. Not necessarily panic, but think about it. 100 milliwatt, 200 milliwatt, yeah, that's fine. If it's one of those BC639s, which is a small power device in the same package, 500 milliwatts is okay. TO220, which is your typical 5-volt regulator, 800 milliwatts, yeah. The case is going to get hot to touch at that stage. But beyond that, think about using a heatsink. We did do a presentation here years ago about heat sinks and heatsink design and calculations, which half the people weren't even here then. Maybe we'll do another one, John, sometime.
On our website somewhere.
Yeah. Did you do it, or did I do it? Or yeah, you did one. Yeah, yeah. And we were talking solid-state relays. These guys need heat sinks as well. This thing, I don't know what that one's rated. I just found a picture on 40 amps. You try putting 40 amps through that sucker without putting on a heat sink, it's going to be bye-bye Cridum very quickly. Doesn't matter how good the brand is. It's going to die. That's why it's got under here a solid metal plate with screw holes. It can't hang in midair. So you need to go and read the data sheet, and it'll probably say mount on a heatsink with a thermal resistance of 1.5 degrees C per watt to ambient, or something like that, or here's some curves with a fan, what have you. Cridum are the kind of the benchmark in solid state relays. Fing Wang Gong is not. And there are plenty. We've had stories in this room of was it you, Rob, of buying solid-state relays at some stage? And some of the ones that arrived were just shonky as. Was it you or someone else? No, not you. Yeah. No. No. He's got nothing to say. It's okay, Steph. Nothing meaningful to say. And I think that's the end.